Could Earth be signaling an immense internal adjustment? Within a single span of 24 hours, 4 powerful earthquakes jolted the planet's crust across widely separated regions. A magnitude 7.4 tremor east of Davao, Philippines. A magnitude 6.3 quake southeast of Lorengau, Papua New Guinea. A magnitude 6.7 follow-up shock near the same Philippine trench. And finally, a magnitude 7.6 rupture deep under the Drake Passage, between the southern tip of South America and the Antarctic Peninsula. In a world where every major geological shift is instantly mapped and measured, such a concentrated burst of seismic energy raises the inevitable question: are these events independent coincidences or subtle signs of a more complex global tectonic adjustment? And if so, could they be indirectly setting the stage for heightened volcanic activity elsewhere? To unravel the mystery, one must view the planet not as a collection of isolated faults, but as an integrated dynamic shell, its lithosphere broken into plates drifting over the ductile asthenosphere. These plates, roughly 100 kilometers, 62 miles, thick on average, are constantly in motion. When friction locks them temporarily and then suddenly releases, earthquakes occur. But their effects, both static and dynamic, ripple across vast distances, sometimes reaching volcanic systems that are already under pressure. The 4 major tremors of October 10, 2025 form a chain in time, but not in direct geological connection, yet each plays a role in redistributing the stresses that define our planet's ongoing tectonic balance. The sequence began at precisely 1 hour and 43 minutes past midnight, Coordinated Universal Time, when a magnitude 7.4 earthquake struck about 20 kilometers, 12 miles, east of Davao, southeastern Mindanao, in the Philippines, at a depth of roughly 58 kilometers, 36 miles. This region lies at the complex interaction between the Philippine Sea Plate and the Sunda Plate, an area marked by subduction, crustal compression, and arc volcanism. Here, the oceanic lithosphere is forced beneath the overriding plate, generating deep-seated stress accumulations. The rupture's focal depth places it within the subducting slab, rather than at the interface, a typical feature of intermediate-depth earthquakes in this tectonic corridor. Its mechanism was primarily compressional, consistent with the downward bending and internal fracturing of the descending oceanic crust. Barely 20 minutes later, at 2 hours and 8 minutes UTC, the ground shuddered again, this time farther east, near Papua New Guinea. The magnitude 6.3 quake occurred roughly 134 kilometers, 83 miles, southeast of Lorengau, at a depth of 10 kilometers, 6 miles. Unlike the Mindanao event, this one was much shallower, taking place along a transform or oblique slip segment of the Bismarck Sea Plate boundary, where microplates jostle in a mosaic of strikes and subductions. The shallow focus implies brittle failure within the upper crust, potentially linked to local stresses transferred from the adjacent subduction arc. Though smaller in magnitude, the shaking intensity here was locally severe, demonstrating how even moderate crustal ruptures in tectonically active zones can unleash massive amounts of energy. Roughly 9 hours later, the Philippine trench shook once again. At 11 hours and 12 minutes UTC, a magnitude 6.7 earthquake struck only about 23 kilometers, 14 miles, east-southeast of Davao, southeastern Mindanao, at 61 kilometers, 38 miles deep, practically in the same subduction environment as the earlier 7.4. The proximity in both location and depth suggests this was not a random occurrence, but likely an aftershock or triggered event within the same slab segment. Such sequential ruptures reflect stress redistribution. When one portion of the subducting plate breaks, the release strain can shift to nearby regions, loading them to their failure point. In this sense, the 6.7 acted as a mechanical echo of the earlier, larger event, a further release of stored elastic energy within the downgoing Philippine sea plate. But the day's seismic crescendo was yet to come. At 20 hours and 29 minutes, UTC, deep beneath the icy waters of the Drake Passage, the crust heaved with a magnitude 7.6 earthquake centered near 60 degrees south latitude and 61 degrees west longitude at a depth of about 8.8 kilometers, 5.5 miles. The Drake Passage, a narrow marine corridor between Cape Horn and the Antarctic Peninsula, is not merely an ocean gateway. It is a zone of significant plate interaction, where the Antarctic plate slides past the Scotia and South American plates in a predominantly strike-slip motion. This event's focal mechanism suggests left lateral slip, typical of transform boundaries. The crust here is relatively thin, fractured and cold, yet the tectonic velocity gradients are large, producing stresses sufficient for strong, shallow earthquakes. The seismic energy released under these polar waters propagated through both crustal and mantle pathways, subtly altering regional stress fields across the southern oceanic lithosphere. At first glance, these four quakes appear scattered and disconnected, separated by thousands of kilometers and miles of ocean and continent. However, the timing invites analysis through the lens of global stress coupling and the phenomenon known as dynamic triggering. When a large earthquake occurs, it emits not only static stress changes localized near the rupture, but also powerful seismic waves, compressional P, shear S, and surface waves that travel through the entire planet. These waves momentarily distort the crust and mantle, altering stress conditions in distant regions by fractions of a megapascal, tiny compared to local tectonic loads, but occasionally enough to disturb a fault or magma system already at a critical state. The sequence of 4 large quakes within 24 hours could therefore represent a cascade of independent events, coincidentally close in time, or a subtle global response to cumulative transient stresses. In fact, geophysical models have demonstrated that high-amplitude surface waves from one major quake can instantaneously affect stress regimes in another hemisphere. For example, following the 9.1 to 9.3 megathrust event off Sumatra in 2004, measurable changes in stress and microseismicity were observed as far as Alaska and Japan. The mechanism is not a domino chain in the literal sense, but rather a planet-wide resonance effect, where transient oscillations of the lithosphere may perturb distant faults, particularly those already near failure. In that light, the October 10th sequence may reflect a period during which several major faults were critically loaded. The initial Philippine rupture possibly rebalanced stresses along nearby subduction boundaries, while the later Drake Passage slip might have been influenced by accumulated global strain from months of Antarctic South American plate adjustment. Even so, correlation does not equate to causation. The energy released by the Philippine earthquakes, while immense, diminishes rapidly with distance. By the time seismic waves reach other continental margins, they are largely dissipated. Thus, while it is scientifically plausible that some distant perturbation contributed to fault destabilization elsewhere, Most experts interpret such sequences as random clustering, the natural rhythm of a restless planet constantly balancing its internal forces. Still, one cannot discuss such powerful seismic bursts without acknowledging their potential implications for volcanic systems. Subduction zones like those off Mindanao and Papua New Guinea are also the cradles of active volcanism. The sinking slabs generate magmatic fluids through the dehydration of minerals, fueling the magma reservoirs beneath volcanic arcs. Each significant tectonic jolt can modify the stress regime around these reservoirs, sometimes hastening magma ascent, though usually by small margins. When combined with ongoing micro-seismic swarms in other parts of the world, notably beneath the Cascade Range of North America, it becomes natural to ask whether the mantle itself is undergoing a broader episode of agitation. Recent microquake clusters beneath Mount St. Helens, Mount Rainier and Mount Hood underscore this curiosity. Hundreds of tiny tremors, most below magnitude 1, have been recorded in these areas, accompanied by slight ground deformation detectable only by sensitive GPS arrays. Although the magnitudes are minuscule compared to the Philippine or Drake events, their presence signals minor readjustments in the crust above magma reservoirs. These volcanoes are part of the Cascade Arc, formed by subduction of the Juan de Fuca Plate beneath the North American Plate. While each edifice has its own distinct magma system, deep seismic tomography reveals a diffuse hot zone at depths exceeding 25 to 40 kilometers, 15 to 25 miles, connecting partially molten regions beneath the arc. This does not mean the volcanoes share a single chamber. Rather, it suggests a network of interconnected conduits through which heat and volatiles migrate. Disturbances in this network can subtly influence regional magmatic pressure. If the recent global seismicity were to alter stress in the mantle wedge feeding Cascadia, the effects would likely manifest as small perturbations, slight changes in the rate of gas release, melt segregation, or local crustal microfracturing. These would not instantly produce an eruption, but could gradually modulate magma movement over months or years. Thus, the link between earthquakes and volcanism is not direct or deterministic, but conditional. It depends on whether the underlying magmatic system is already close to eruptive threshold. And history offers precedent. There have been rare but notable cases where large earthquakes indeed triggered volcanic eruptions or accelerated unrest. These examples will form the foundation for understanding how the recent October events might, under specific conditions, influence volcanoes worldwide, from the subduction arcs of the Pacific Ring of Fire to the simmering calderas beneath the American Northwest. One of the most significant examples is the Cordón Caulle eruption in Chile in 1960. Which followed the magnitude 9.5 Valdivia earthquake, the largest ever instrumentally recorded. Within approximately 38 hours after the main shock, a fissure eruption began at Cordón Caulle, ejecting vast amounts of basaltic and rhyolitic material. The temporal proximity and the regional strain redistribution strongly suggest that the earthquake triggered decompression in a magma reservoir that was already volatile, rich, and overpressured. This event demonstrated how an immense tectonic rupture could shift local stress fields enough to unlock magma pathways and release accumulated gases. A similar mechanism was inferred during the 1975 magnitude 7.7 Hawaii earthquake, which preceded increased activity at Kilauea's summit. In that case, ground motion and pressure redistribution caused by crustal flexure altered the magma conduit geometry within hours. The Hawaiian system, unlike subduction arcs, sits above a mantle plume where magma supply is steady and persistent. When an earthquake modifies the confining pressure, even slightly, it can facilitate magma ascent toward the surface. This interplay between seismic deformation and internal buoyant forces exemplifies how local crustal shifts can temporarily destabilize a magmatic system. Another prominent case is the 2004 Indian Ocean megathrust earthquake, with a moment magnitude of about 9.1 to 9.3. The immense static and dynamic stresses from that rupture propagated over thousands of kilometers, miles, and subsequent observations indicated enhanced unrest at volcanoes such as Mount Talang and Mount Loisa in Sumatra. Researchers later described these responses as dynamically triggered. The intense seismic waves cause microfracturing and gas exsolution within magmatic systems already approaching eruptive conditions. While no global volcanic chain reaction followed, localized increases in activity underscored the capacity of seismic energy to disturb near-critical systems, especially in subduction-related environments. A classic historical example is Mount Fuji's Hoei eruption in 1707, which occurred weeks after a magnitude 8.6 to 8.7 earthquake off the Tokai region of Japan. Stress modeling of that period suggests the megathrust event altered the regional strain field in a way that encouraged magma ascent beneath Fuji's edifice. The delay between quake and eruption, spanning several weeks, demonstrates that triggering need not be immediate. Static stress changes, once imparted to the crust, can slowly propagate through magma-filled fractures, promoting gradual overpressure until the surface ruptures. The phenomenon highlights how volcanic systems respond on variable timescales, depending on their internal pressure and conduit permeability. More recently, in July 2025, a magnitude 8.8 earthquake in the Kamchatka region was followed within days by eruptions at several volcanoes, including Krasheninnikov, Kluchevskoy, and Shiveluch. The clustering of eruptions after a major tectonic release renewed interest in earthquake-volcano interactions in the modern context. Preliminary interpretations suggest that both static stress transfer and dynamic shaking may have temporarily opened magma pathways or altered degassing behavior in systems already at near eruptive equilibrium. Likewise, the 2005 Nias Simeulu event in the Lake Toba region was linked to post-seismic activity within the vast Toba caldera, evidence that even massive caldera systems can respond to external tectonic stress shifts. Taken collectively, these events reveal that earthquakes can indeed act as catalysts for volcanic activity under very specific conditions. 1. When a magma chamber or conduit is already primed with volatile pressure near the breaking point. 2. When the stress changes caused by the earthquake, whether static or dynamic, are aligned with the direction of magma ascent. And 3. When the mechanical strength of the surrounding crust is sufficiently low to respond to such perturbations. Without those preconditions, the effects of even a massive earthquake dissipate without consequence. From a purely geophysical perspective, the process can be simplified as follows. The passage of seismic waves transiently alters the lithostatic and confining pressures in a region, producing momentary oscillations of stress within the crust. If those oscillations intersect a magma-filled fracture, they can induce temporary pressure drops or promote volatile exsolution, both mechanisms that enhance buoyancy. Alternatively, the permanent deformation from static stress transfer can reduce the overburden pressure on a chamber or weaken the structural integrity of a conduit. In systems teetering at critical pressure, these minute changes can serve as the spark that triggers eruption. However, where magma remains deep or poorly connected, the same seismic impulse passes unnoticed. Applying this understanding to current global activity, it becomes clear that the recent cluster of large earthquakes, from the Philippine subduction zones to the Drake Passage transform fault, is not in itself a direct forecast of imminent eruption. Yet the cumulative energy release subtly reshapes the stress distribution across numerous plate boundaries, and within those broad regions, specific volcanoes already under strain might respond in the coming weeks or months. The key lies not in the magnitude of the quake alone, but in the internal readiness of the magmatic systems it influences. The ongoing microseismic swarms beneath the Cascade volcanoes of North America remain an excellent testing ground for these dynamics. Although the current activity there is well within background levels, the deep hot zone beneath Mount St. Helens, Mount Rainier, and Mount Hood represents a reservoir complex sensitive to long-term stress accumulation. Continuous monitoring through GPS deformation networks, seismic arrays, and gas emission sensors will determine whether subtle signals evolve into something more significant. For now, the tremors remain whispers rather than warnings, but Earth's internal dialogue never truly ceases. In the broader sense, these interactions between quakes and volcanoes remind us of the profound interconnectedness of Earth's systems. The crust, mantle and core operate as a living continuum of motion, exchanging energy through fractures, melts and waves. Every great earthquake is both a release and a rearrangement, sometimes awakening dormant systems, other times restoring equilibrium. Ultimately, while the current seismic burst underscores the planet's vitality, it does not foretell catastrophe. Vigilant observation, not fear, remains the proper response. The Earth is restless, but restlessness is its natural state. Every tremor, every distant rumble beneath ocean or mountain, is part of a grand geodynamic conversation, billions of years in the making, a conversation we are only beginning to understand. So, if you found this deep dive into our planet's mechanisms enlightening, don't forget to like, share and subscribe, and tap that hype icon to help this video reach a wider audience. The more people understand how the Earth truly works, the better we can appreciate both its power and its balance, and the more prepared we become for whatever the planet decides to do next.